for next few sessions we'll try to revise the content we learned so far, and that will help us put us in a better position to go for the intermediate concepts and even the advanced concepts in the physical design course. So what I'm gonna do is to revise briefly all the topics and touch upon the basics, fundamentals, and some key points that we always talked about. So this will help you to revise your content, and immediately after I would like to put you all through a short test, because that's how I conduct the course, my course. And with that I would be able to test your knowledge. It would be an open book test. Also you can refer your material, content, everything that you have, all the resources, and accordingly I would expect you to answer the questions, because those are very important questions. If you are able to answer it, it means you are on a positive track towards achieving your goals. So, and this would also help, this revision would also help. It is expected that those who joined late or those who missed few of the sections, already they joined earlier but they missed few of the sessions, then for useful for them also. So I hope you will equally participate in these particular sessions to answer me queries. If you couldn't answer, don't want to answer, but I would still encourage, try to answer. Okay, so we'll see one by one how we go ahead with this. So what we have learned so far, we have learned about the transistor as switches, transistor as logic gates, transistor, and then the fabrication of CMOS transistors, how we can fabricate those transistors on silicon wafers and using the photolithography process. So these basic things you should know. So if you recall, I explained you okay, the switches here, then the logic gates, we also know NMOS and PMOS, how they work, the latches, then we also understand a bit about the flip-flops. Okay, because using these latches and flip-flops, we call them as a sequential circuits. The logic gates, we call them as a combinational circuits, right? So combinational circuit, we saw that the output depends only on the present state, but in the sequential circuits, we see that it has a memory. It means the output depends on not only the present state but also the previous state, what was the previous input to the circuit. And fabrication of the CMOS transistors on the silicon wafers, where mass transistors are mass produced in large numbers and using the photolithography process. So briefly, what is the photo? Photo means light, lithography is the printing way of the transistors are fabricated. I briefly explained you that okay, we had this silicon substrate, that is P substrate, okay, and then we have this silicon dioxide somewhere, we call it as a SiO2, and we want to fabricate the transistors here. So many layers are there. We know what layers are there: P plus, N plus, poly, metal, right, and the contact. These are the layers are there. Okay, so first of all, if I want to fabricate an N well in P substrate, I have CMOS transistor. It means I have NMOS and I have PMOS. Both of the transistor I want to fabricate in this P type substrate. It's a P type semiconductor. So I know that what I will do, this is the SiO2, and then I will deposit one more material that I call as photoresist. This is photoresist. So it's a thin organic polymer. If you recall the concept, I said that this is the thin organic polymer that acts to help us fabricate the particular layer or particular division in a specific area of this wafer. So here is somewhere I want the N-well to be fabricated. So what I do is that I will use the N-well mask. I will use the N-well mask. So N plus is the layer I want to use. So basically these are the masks. So what I do here, I have this somewhere. I have the mask. This is called as mask. So the purpose was, then I will expose the wafer, the whole wafer, through the called as ultraviolet lights, UV lights. Okay, and this wafer is exposed to UV, to UV, to UV, right here. So because of this action, what is happening here, the area which I covered by the mask, this area, the light is not allowed to pass through it. Okay, depends on what action. In other areas the light got allowed to pass through it. This is the one type of mask. But I explained you, there is a way, there is also a mask where in this area only I am allowing the light to pass through the mask, and the other area light is not reaching to the mask, to the photoresist here. So through the mask the light passes here, and this portion of the photoresist gets softened, it melts away, right? So it melts away, so it means the new type of wafer or the new type of structure that I will have here would look something like this because of this action. So the portion here is gone, and what I am left here is this one. So only this portion the photoresist remained, and the remaining photoresist got melted away, softened, right? So then I put this wafer, in the hydrofluoric acid, which will etch the oxide in this region, because you see this is the silicon dioxide, SiO2, right here. If I use the right ink again, this is SiO2, right? So how the wafer looks like, then it looks like this: p-type substrate again, and then I have this, and the oxide will remain because the photoresist is still there, the oxide in this region, but here the oxide is gone because of the hydrofluoric etching. So you see now this is SiO2 and this is my photoresist, and here oxide is gone. And then I use the ion implantation method or diffusion method to fabricate N++ or N++ region. So I will call it as a process in which I fabricate the N-well. Something looks like that, square diagram, right? So similarly I explained you, just a second. Right. So I explain you all the procedure. We will repeat the same procedure to fabricate each and every region in the transistor wafer, in the silicon wafer, to fabricate these transistors, right? So just as a layout engineers or as a VLSI engineer, you need to know these basic steps, even not in detail, but having understanding of what is mask, what are the layers, and how the basic transistors are fabricated will help you to understand it at a bigger level. So then I told you about CMOS transistor layout, how we can actually fabricate the CMOS transistor. Right over here. Okay, so you see now this is the top view of our structure. If you recall from the previous concepts, I said that this is going to be the top view. This is going to be the top view. So it's like this is the CMOS transistor layout. So it shows me that I want to lay out my transistors, both NMOS and PMOS. And by doing so, what I'm exactly doing is I'm just specifying these rectangles. So first rectangle shows me this is the rectangle of N-well. So this is how it looks like. Then second rectangle looks like polysilicon. Third rectangle looks like it is of N plus diffusion, and another rectangle is of P plus diffusion. Then I have final rectangle contacts and the metal. So these are the rectangles that I am using. So how I am using it? So you see, just for to understand, I have represented them with different colors. So for example, this is the N-well that I am depositing here, that I am putting here. So that's the mask for the N-well. So when I am exposing this, so let's say this is the wafer actually. Now we are looking from the top view, not the cross section. So first I will have this mask and I will let the light pass through it. Then the light passing through this mask will melt the photoresist beneath, and after that I know that the photoresist will melt, and that area I am able to diffuse the dopants. So this is how I will use N-well mask to create the N-well here. Then I know that this is a schematic of this is the layout of CMOS inverter. So where is the NMOS transistor? Here. That is the source and the drain. And where is the PMOS transistor? It is sitting inside the N-well. So that's the drain and the source. So again, let's come back here. You see now, this is the way I will create this is called N diffusion area, N plus diffusion area, because this is where my transistor is fabricated, NMOS. And now to isolate the source and the drain region, here is the poly mask that I am having. So look at their position. So when I am having this poly mask right here, I already got source and drain separated, and this is how NMOS got fabricated right over here. Look, this poly crossed over that one. Okay, so this is basically a physical layout, physical design of a CMOS inverter. So source and drain are isolated as soon as I draw the polysilicon. Same here for the PMOS. As soon as I have drawn the polysilicon, drain and source of this PMOS transistor, which is sitting in the N-wall, is separated. And look at this one, the dimension and the orientation. This is same over here. But where is this blue P diffusion region for the PMOS? Here is the P diffusion region right over here. So this is the mask for the P diffusion area where my PMOS is to be fabricated. So you see now, and now I know that CMOS inverter drain and the source of this transistor. Let's say this is source or this is drain and source. This is symmetric device, so it doesn't matter. So this is drain and drain, they are shorted together, and that is the output terminal of the circuit. And then I know that two gates are connected, so this is the input of the circuit. So once that is done, why do I have this extra N plus diffusion region just next to this NMOS? Because this is the P diffusion region actually. Where is the P diffusion region? Let us come here. Look at this. This is the P diffusion region which is just sitting. So this is P plus. So this is the access to P substrate for the NMOS, and I want N diffusion region in the N-well also. So here, right over here. So this is giving me access to the N-well, because this region is the body of the PMOS and this region is the body of NMOS. So we know that in the schematic representation, this is drain, this is source, this is gate, and the body I will show like this, which is tied to source. For the PMOS, I know it is shown by the bubble. So this is source, this is drain, this is gate, and the body I am tying to source again. So I will show symbolically this is NMOS and this is your PMOS. So this is how, that's why we create these regions right over here. And once that is done, everything is done. So I am just going to erase this all. So what I want now, access to this, I want wires to connect to each of these terminals, just like you create a circuit on a breadboard or PCB. So I define these contacts in the areas I fabricated. So you see now these contacts are here. Basically they are giving me access to this, connect to the source and the drains, again source and the drains, and the body of those transistors as well. Once that is done, I will just pour all the metal, all the metallization right here. This metal is all the way like this, and this metal is all the way not up to here, from here up to here actually, and like this. So you see, if you come down, these layers are here. If you come down, this layer, this is the mask for the metal. So this is how I will understand how the basic layout is drawn. If I am very good at understanding this layout, I can understand layout for bigger cells where several cells, this is cell for inverter, but there will be several cells for NOT gate, NOR gate, latches, flip-flops, and there will be tens, hundreds of such cells interconnected together to form a bigger circuit. So in that case, if I know how to understand these layers, how they are drawn to fabricate the transistor and hence the circuit, I would be easily able to understand a bigger layout. Okay, so make sure that we are doing. So then we talk about MOS transistor. We understand basic operation about this. We call it as a MOS because it's metal on the top, oxide in the middle, and semiconductor in the bottom. So that is why we call this structure as a metal oxide semiconductor. And we know that it is fabricated or it is designed by superimposing several layers of conducting and insulating materials. So where are the conducting layers? We know that the metal is conductive, SiO2 is insulator, and semiconductor is in the bottom. So it's basically combination of conductor, insulator and semiconductor. Okay, how does it operate? That is the basic question. This is the symbol looks like for the NMOS. This is your NMOS, this is your PMOS. Okay, and now in a bit we'll explain the basic working principle of this. So the body of the NMOS, we call it as a bulk silicon. Another word we use, we call it as a wafer, or another word we use, we call it as a substrate. Same for this case also, right? So we always remember that NMOS is fabricated in P body, PMOS is fabricated in N body. When both of these to be fabricated in single body, then what we do? We take a specific body, and we know that in the P body, which transistor will be fabricated? NMOS. But to fabricate PMOS, we need to create its own body, that we call it as a N-well. And in the N-well, we make PMOS right over here, this transistor. What about we have N body, N substrate, yeah, N substrate. Naturally we are going to have PMOS transistors without any problem, but for NMOS we need to create a well. This well is called as P well, and in the P well then we will repeat the procedure to fabricate the areas using their respective mask. So this is your NMOS and this is gonna be your PMOS, right? So usually you have P substrate or N substrate, and accordingly you guys are there to fabricate your transistors. So let us understand how these two structures basically work. Just revise one more time. So we know that it has three terminals: source, gate, drain. Source, gate, drain. We know that the metal is nowadays replaced by a polysilicon. It is a semiconductor, but it is heavily doped, heavily doped, so that it acts as a conductor. Acts as a conductor. And silicon oxide, it's just a glass, or we can say it's an insulator which is there, okay, and body is the semiconductor, N or P. So what we know here, this structure is fabricated using series of chemical processing steps and photolithography. We just got that. So basically we also know that you have a substrate, and first procedure they do is the oxidation. You know, they put the SiO2 on the top of this, and then they define the areas using the mask, you know, and accordingly that we call it as a selective introduction of the dopant, and then they accordingly create the areas here: NMOS, N plus diffusion, P plus diffusion. We just saw that, and they keep on depositing and etching of the layers, and finally they also deposit and etch the metal and the contacts. So let us understand now how these structures are working. So we know that this N plus and P plus regions. In the NMOS transistor you have N plus regions acting as a source and drain. In the PMOS transistors you have P plus regions acting as source and drain. Remember, the device is symmetric. What does it mean? Can I call this as a source, as I wrote here? Can I call it as a drain, and can I call it as a source? Yes, because it's a symmetric device. Here also I can define this is my drain and this is my source. Okay, so it's a symmetric device. So we'll see that. So as I said, the N plus and P plus regions here, they are heavily doped. That's why we indicate with the plus sign. If I show N plus plus, N plus plus, P plus plus, P plus plus, it means very heavily doped, right? So it depends on how the transistor is fabricated. So we know that this is the wafer that is usually 15 to 30 centimeter in the diameter. Okay, let's say this is 30 centimeter in diameter, and then this is individual dies. So let's say each die is a die of a processor. So it's simple, and in the processor you have millions of logics that we are going to see again ahead, right? So these transistors all are sitting here. So this is the schematic of a single transistor, but inside the wafer there are thousands of such dies. This is called SI die or SI chip, and inside this chip, if you see this is the chip, this is the chip right over here. So you have billions and millions of logic level, millions of logic gates, and billions of transistors. So if we understand the basics of single transistors, layout, schematic, working principles, circuit diagrams, it will help us to step by step decompose these millions of logic circuits and decompose their physical layouts to understand bit by bit. So as I said, the gate is nowadays made of polysilicon, not a metal, and source and drains are interchangeable because of the symmetry of this one. Now the body is typically grounded. It means when I do the circuit, when I design the circuit using these transistors, I will connect the body of the NMOS to the lowest potential in the circuit, usually ground, right? For the PMOS, I will try to connect the body to the highest potential to the circuit. Let's say logic 1. Here it's the logic 0. Why I do so? Because As soon as I make the body connected to the ground, so you see this is N and this is P. This is N and this is P. So do I see that I am having the PN junction diode here? This one diode here, and this is the one diode here, 1 plus P plus, right? So what I see here, if I connect the source also to the ground or logic 0, so basically I avoid the possibility. This is the diode, okay? This is again the diode. I'm telling you very details so that it will help you to understand the parasitics in the layout. Parasitics, okay? That is resistor, capacitors, and you have PN junctions also. You have to understand all these minute details to be a good layout designer and all this. So when I do that, so it means my source and this is the body P, that is the body, okay? So they are both at the ground potential, so I avoid this PN junction from getting forward bias. I don't want this to be forward bias. If it is forward bias, it means the diode is on and the current will flow, right? I don't want that because it will then interfere the operation of the MOS transistors, right? So remember always, the body of NMOS is typically tied to the lowest potential in the circuit. Obviously we know that what is the lowest logic in the digital design, logic 0, and what is the highest logic in the digital design, logic 1, right? So we call it as a high logic and we call it as a low logic. So for the NMOS, the body is always tied to the lowest logic, typically ground. For the PMOS, the body is always tied to the highest potential, which is logic 1. So what I showed you in the previous picture, now remember this again. This picture I called it top view. This is the top view that I explained you. We are looking from the top, just like you are seeing the computer screen. So we are basically looking from the top at it. What about the same? This is the same diagram, CMOS inverter. This is the same CMOS inverter, and this is called as cross section, cross-sectional view. So this is your cross-sectional view, and with this said, you can see that you have all the layers. Just try to understand. So cross-section means I am again looking at my computer screen, but it's a side view, not the top view. If I look from the top, right here, I go and look from the top, then it will be called as top view, right? So I hope you understand between the cross-sectional view or side view and the top view. So look again, we are having the P body in which NMOS is there. Its body connection is also there. I call it this P diffusion area and substrate tap. So I am having access to it. Then I have a separate body in the P body. I have a separate body called N-well for the PMOS to be fabricated. Then I have drain and source in the P diffusions. I want to have access to its body. Then I got another region. I call it the N plus well tap. Okay. Now once that is done, what I see here between source and the drain in NMOS, I have this gate, polysilicon obviously, and on top of that gate I have SiO2. This is SiO2 basically. That is oxide. It's just an insulator to avoid. What insulator does? It avoids the conduction and shorting of one area to another area. So it just isolation. It's just there for the isolation. Here also I have oxide, and here I have spreaded the SiO2. It's just for the isolation, because if I have this, I am making sure the source and drain are not shorted. I am making sure the source and drain are not shorted. That's what I want for the proper operation. Then again here SiO2, SiO2, SiO2. This is all SiO2 or thick oxide. Okay. So once that is done, all I am doing is this metallization. What I'm doing is the metallization. I pour the metal all the way, right here, on even on the gates above here to have the connections. It's just for the connection. So these are the connections, right? These are the connections. This is also the connection, and this one. Okay, and how do I have access to these connection points? Because in the layout I define the contacts. You remember from the top view, here was my contacts, those squared black squares, little black squares. So those allowed me to have access to form the cuts, and when the metal is poured, the metal goes here, and that's how it got connection. So SiO2 layers is visible, N diffusion area is visible, P diffusion area is visible, polysilicon is visible, metal is visible. And look, this drain and drain of two transistors. This is drain, this is source, is NMOS. That is drain, that is source of PMOS. And drains are connected, I call it output terminal. Gates are connected, I call it as an input. This is how essentially my circuit was. If you remember, A, output Y, VDD, and the ground, right? That was drain, source, and the drain. So drains were together, so I call it Y. Gates were together, I call it input way, right? So to summarize, in CMOS technology, we just understood and revised the cross section. The substrate could be N-type or P-type, depends on that. Then with the P substrate, NMOS is built in a special well, in which the dopant atoms are added to form the body of the opposite type. And same here. So let's briefly revise how this circuit works, how this transistor works when we apply voltages or electric field. Apply voltages. So this terminal we defined, we said that it's our magic terminal or the control input. It's just like we put a voltage on top of it, and accordingly the MOSFET will behave. So when we apply the voltage on this terminal, it will control the flow of electric current between source and the drain, right? And the body is generally tied to the lowest potential, logic low. That's what we have said, because I don't want this junction N plus and P, N and P. We know that it's a PN junction. I don't want it to be forward bias for the proper operation of the MOSFET, right? Same here. I will tie the body to the VDD, for example, logic 1, and accordingly I will apply the voltages here. Okay, so let's see how the channel is conducted here. So for example, if I tie the gate terminal to the ground potential, logic 0, and the body is also connected to the logic 0. So I say that in these conditions, my transistor is off. I say that the transistor is off. Okay, now from logic 0, which is the ground potential, I start to increase the voltage. So I have two levels, logic 0 and logic 1. So I start increasing the voltage, and I'm trying to approach from logic 0 to go to logic 1, right? So when I increase the voltage, so it means above 0 I have a positive voltage, so I am depositing the positive charges here. So I know that this is the P semiconductor, so it has lot of positive charge carriers and only few negative charge carriers, right? So once the gate voltage is increased, what happens is that an electric field is generated across this MOS structure. Electric field is generated, and this electric field attracts your free electrons in the P body. So they start to come over and they start to populate in this region, right? Even though they are small in number. So this they say that, we say that they start to gather underneath the silicon and the SiO2 interface, which is this line, okay. And if we keep on increasing the gate voltage, if we further increase the gate voltage so that they have more number of charge carriers, then the electrons in the p type of semiconductor, they also increase in number. So when there are sufficient number of charge carriers, we say that electrons in the p type semiconductor are now higher than the holes, number of holes. So we say that number of electrons are higher here than the number of holes. We say that the channel is inverted. So under this thin region, now you have a lot of electrons because of the positive voltage. So we say that this portion is become from p-type semiconductor to the n-type semiconductor. And once that is done, so let's say you have positive voltage here and this is also negative voltage. So logic 0 and logic 1, right? So what you have, once your channel is formed, you have the conduction path of electrons from source to drain, right? We always know that the electrons flow from the negative terminal to the positive terminal, right? So we say that the conduction path of electron carriers is formed from source to drain, or we say that the current starts to flow from drain to source, because the current will flow from the, let's say this is the circuit, so we say that the current is flowing from positive terminal to the negative terminal, right? This is how this works, and in this condition we say that the transistor is on, right? So that was there. Let us understand the same working principle for the PMOS transistor. So body, let us say it is tied to logic 1, highest potential in the circuit. Always remember that for the NMOS, where we tie the body, lowest potential, logic 0. For the PMOS, we tie the body, that is N-well, to the highest potential in the circuit, that is logic 1 or VDD, right? So now if I apply a gate voltage, if I apply a positive voltage on the gate terminal, right? So what will happen? The transistor is off because the body is connected to the logic 1 and I am also applying a positive voltage right here, right? But what if from positive I come to 0 volt here and again I reduce the voltage so that I apply now negative voltage. So from positive I am going to the negative voltage. Now this is an n-type semiconductor, so I know that there are a lot of electrons here, and few positive charge carriers which are holes, right? So if I keep increasing this negative voltage on top of the gate, these positive charge carriers come over here because the electric field is generated, and the higher the electric field, these charge carriers come right in the SiO2 and the silicon interface. So I say again that at this interface, which is interface of Si, silicon, and SiO2, silicon dioxide, I know that the number of holes now because of the voltage are higher than the number of electrons here. So I say that the channel is inverted and the conducting path of positive charge carriers is formed from source to gate. So if I have like negative voltage, it would be all opposite to NMOS, right? We applied the positive voltages there. Here we'll have a negative voltage. So if let's say this is negative and source is connected to the positive, right? So the holes are traveling from source to drain, right? In this way, and the transistor is on. So we'll say that the current also is traveling from source to drain. Same here. Okay, and this is the case when we declare the transistor is on. So just remember these basics that will help you to quickly understand the polarities and what voltages to be applied, how transistor turns on and turns off, what is the body voltage and all these things, because these are very important concepts. Then just have a quick look. We know now what the symbols look like. This is the symbol for NMOS, this is the symbol for PMOS. If you see the symbols of the transistors like this, which is your drain, this is source, and this is your gate, and the body is doing like this, so you can see that this is the symbol for NMOS, right? And what about this one? Your source, your drain, and this is gate, and I say that you have this this is how the arrow is shown. So sometimes you see this arrow direction, it is shown like this. So there is sometimes the way this is how the symbols are shown. So just remember, when you see a bubble, you have this PMOS, and when without a bubble, this is of NMOS. And we know now that we
Sir,
can
in
use
PMOS, the arrow is inward, right?
what?
In PMOS, that arrow is inward direction, right?
Arrow is
Inward direction, right? It is opposite, right?
there is one more. I see that when you don't show a bubble actually,
Uh,
then it is this is drain, this is gate, this is source, gate, and drain. So this is how I think this is shown like this. So this is one way of representation, and here you don't show arrow basically. Okay, here you don't show arrow, just tie the body like this. So I'll explain you in a moment. Like this, and this is like this. So the body is connected to the source. Here the body is connected to the drain. Body is connected to the source. No. It's for the NMOS. Like this. Just show like this. And this is another pair. This is one way of representation. This is another pair. Right? So for the NMOS, the arrow is shown outward. For the PMOS, arrow is shown inwards. It just shows the direction of the current. You see, if you arrow is outward, the current is flowing from drain to source. For the PMOS, when the arrow is inwards, the current is flowing from source to drain.
okay, sir.
Okay. So now we know that when the gate is at logic 0, we will declare NMOS to be off, and this is how we would prefer to show it. When gate is at control 1 or logic 1, we will say the NMOS is a closed switch, and we will show this way. For the PMOS, when the gate is at logic 0, we will say the transistor gets on, and this is how we will show it's a closed switch. When the gate is at logic 1, we say the PMOS is off, and this is how we will show the switch logic, switch representation. And remember, VDD or the power is the logic 1, and VSS and the ground is logic 0. So again, we know that this was our concept for the CMOS logic, the very first logic we saw. Okay, we understood how the transistors are fabricated, what layers, what mask, what is photolithography, everything, and then we understood their switching action and their operation, how they use as a switches. Once we got that through, we just tried to put a simple circuit. We got PMOS here, and we got NMOS here, and this is how. And we say that this circuit acted as a inverter logic. What is the inverter logic, or in other words, NOT gate? So that's, we call it as a unit cell. Always remember, this is unit cell, just a simple cell of inverter. This is how the symbol is that, and it says that Y is the inversion of A. So A is at logic 0, Y would be 1. A is at logic 1, Y would be 0. How? In terms of switches. So let's say if it is logic 0, this NMOS we always call as pull down network. PMOS we call pull up network. Why we call it as a pull down network? Because when we have a logic 0 here, or let's say logic 1 initially, so the circuit can be drawn like this. So I know that my transistor, which transistor is going to be on? NMOS is going to be on and PMOS is going to be off. So this is how I will call the logic. That was Y, and this is ground, that is logic 0, and this is VDD. So what I see that with the logic 1 at the input terminal, the output got pulled down to the 0 logic or ground level. So that's why I declare NMOS will act as a pull down network. When A was connected to logic 0, I would draw the circuit diagram to be like this. So PMOS got turned on and NMOS got turned off. So that was output. This is VDD, this is ground. So I will say that output got pulled up to the logic level high, that is VDD, and that's why I will say that the PMOS was acting as a pull-up network. So then I understood, and then we saw that whenever I want to make some logic circuit, design a logic circuit, I will use NMOS transistors as a pull-down network, and I will use PMOS network as a pull-up network, right? And I also informed you how about I switch the positions of these two NMOS and PMOS. For example, NMOS I take it to the top and PMOS I take it to the bottom. So one of you submitted me an assignment of the logic gates using NOR, NAND. So somebody connected PMOS in the pull down network fashion, and the person connected NMOS in the pull up network, for the pull up network. Again I repeat, the person connected PMOS logic, no matter it's inverter, NAND gate, NOR gate, for all the assignment that I gave. So you should not connect the PMOS for the pull down network and NMOS for the pull up network. Just do the way it is shown here. Although the circuit will work, like we saw, the circuit will work, but this wasn't a good design strategy. Not a good design. Why? Why? Because, can anybody tell? We want the strong logics, strong levels, logic levels, logic 0 and strong logic 1. And those levels at the outputs are supplied by the power rails. What are the power rails? VDD and the ground. These two supply rails are responsible to throw the output to pull up like we see here, or to pull down right over here. So always it is preferable to have a pull NMOS in the pull down network and PMOS use it for a pull up network. No matter you are creating NOT gate, NAND gate, NOR gate, or even the AND gate, OR gate, and any logic, right? And we will also explain as we progress ahead why they will produce the degraded logic. They will work. It will also give you Y equals to A bar, but the Y equals to A bar would not be, Y output will not be a strong logic level. It would be a degraded logic. It means I want a logic high at the output because of the switching, but I will have a slightly below level than the VDD. So if I am operating 1 volt as a VDD, I will have 0.9 volt. Similarly, I want a strong logic at the output. When the switching happens, I want a 0, that is ground, right? But I will have a slightly above level. It will not reach to the ground. So it will be, let's say, 0. Some points, not between 0 to 1. What could be the logic? It could be 0.1 or 0.2, something like that, not the full logic at the 0. So this is called as degraded logic. So I'll explain a little more how the degraded logic is produced when you when you swap the position of pull-up network and the pull-down network. So once we understood the CMOS NOT, we went on to construct the NAND logic. So we used the concept, we defined the concept of compound gate. Compound gate or compound logic. What is compound logic? Compound logic is a combination of series and parallel combination, series and parallel combination of NMOS and PMOS switches. Right, we know that they work as the switches and we got them series into and parallel. So how we, for example, I wanted to create the 2 input CMOS NAND logic. So I know that NMOS, they got in series here, and the PMOS would be just because they got in series, I got the PMOS in parallel, and this network was pull-up network, this network was pull-down network. And again, I successfully saw that when I have a particular combination of A and B, so I have 2 inputs, so 2 to the power 2 was 4 input, 4 combinations of input were possible. So from 0 0 to 0 1 1 0 and 1 1, I just analyzed this circuit, how this works. So we know that for the 0 0, NMOS network is gone and PMOS switches are on, so output got connected to VDD. Right, so pull down circuit got off, pull up circuit got on, and output got connected to logic 1. For all other possible combination, I just analyze the circuit, how it's working, and that's how I fully understood the CMOS NAND logic. I don't think I have a need to explain you all this combination. You just apply these inputs here and see which transistor is switching and how output is pulled down to 0 or pulled up to VDD. Right, that was the symbol of the NAND logic, 2 inputs, and this is called as bubbled AND logic. All right, so this is we also saw that by using De Morgan's theorems how we can represent that one. Okay, so summary: 2 series NMOS and 2 parallel NMOS gave us NAND logic. And NMOS was our pull down network, and it was responsible to pull down the output to ground when the switching happens. PMOS network was our pull up network, and it was responsible to connect the output to logic 1. Similarly, we analyzed the NOR logic. I said you that okay, 2 NMOS now in parallel here, and that's complementary. We use the word complementary. So complementary in the sense, if this is A, its complementary is A bar. If the signal is B, its complementary will be B bar. So again, it's 2 input here. We got all the combinations. Whatever combinations we apply here, A and B, we could now easily analyze how the switching happens and how output is either pulled down to logic 0 or it is pulled up to logic 1. Is the swapping of the pull down and pull up possible? Yes, possible, but that would be called as bad design. Why? Because output will appear with the degraded logic. And we don't want that. We want strong output levels. When the switching happens, we want strong 0 and strong 1. That's it. VDD 0. We don't want slightly degraded than 1 or slightly above the 0, right? So NMOS again, pull down network here, PMOS again, the pull up network. Now we always understood that there are only two levels, logic 0 and logic 1. And this happens when the transistors are either on or off. So at a time we saw that one transistor is on and other is off when the logic level is applied, right? What if both pull up network, no matter it's an inverter logic, NAND logic or NOR logic, any logic, what if both pull up and pull down network are off? Both are off, switched off. Something happens that PMOS here is also goes into off position and MOS also goes into off position. Same here, off, 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 off. Then the output goes, the logic at the output is called as high Z or high impedance. It's neither logic 0 nor logic 1. We say that it's floating. We just say that it's floating, and usually we just try to then connect it to some logic either 0 or 1. Okay, so that's how, remember that there are two logic levels, but there is another logic level that is called a high Z, and usually high Z can happen if the switching network is completely off. Every transistor in a switching network, in a CMOS, when we talk CMOS, it will remember always have PMOS and NMOS, and they are both off. So in that case, you goes to the state called as high Z. What about the situation where both pull up network and pull down network, here, some logic happens here so that both transistors are on. Here also these transistors are on, this transistor is on. Something happens, usually it is not possible because you have a well-defined logic here, you define what to put here, but sometimes, let's say, things, logic switching happens, both transistors try to go on. Okay, so that condition is unwanted. What is the logic that comes here? The y equal to x is unknown, and you don't want that, right? So usually that doesn't happen, or you avoid it. So pull up and pull down network, remember, are simultaneously turned on, then unknown state can exist, which is unwanted. So to summarize the transistor switching, you see here CMOS logic, gate 1, gate 2 NMOS in series. Here is the A, here is the B. A connects to B, depends on what is available at the gate, which logic is available at the gate. So let's say two transistors NMOS are in series and both gates are at logic 0. So with logic 0 NMOS are off, we know that, this is how. So we say that both switches are off. Same you would see now, if gate 1 G1 is 0 and G2 is 1, the bottom switch is shown to be connected and the and the top switch is off, and you can see for other combinations when both gates are at logic 1 and so on. What about the PMOS in series? Same situation. You just apply, two inputs are shown, two gates are shown here. So four possible combinations are possible. 0, 0, 0, 1, 1, 0 and 1, 1. You apply those and analyze for each combination how the switching is happening. Very easy. Series and series. What about NMOS? Gate G1 and gate G2 here, and you see there is a signal here. Let's say some logic is available here at A, and logic it has to reach to level B, right? And that can happen based on the G1 and G2. So let's see where A tries to connect to B at what possible combination. So when G1 and G2 are 0 0, we see both switches are open. So A is not connected to B. When G1 is 0 but G2 is 1, we got this switch on and A is reaching to B through this line. Here is the connection. Similarly, we see now A is reaching when G1 is at logic 1 and A is reaching B when both switches are on, and that's how we see that. Similarly, PMOS in parallel, we saw that A wants to reach to connect to the B, depends on what is available at the gate control. So when both logics G1 and G2 is at logic 0, we got to see that A is connected to the B. A is connected to the B again when G1 is at logic 0 because this transistor is on, and so on. So you should be able to construct any kind of logic and analyze the behavior through the switching diagram. Okay, so that was all for today's revision, and we'll again now explain what latches are, what flip-flops are. I will introduce some bigger circuits again to help you understand both at the logic level, circuit level and the layout level. So you have any questions? Let me know.